Hello, my name is Jolina Ager, and this is my Physics 2 Lab 2, the magnetic field of a bar magnet. So first we'll start with an introduction, where we'll go over the goals, key findings, background, and then some assumptions made. So the experimental goals, the main purpose of this lab is to measure the magnetic field produced by a bar magnet, to understand its dependence on distance. This will be done by two primary methods, the first being measuring distance using an experimental setup, and the second being using a VPython computational model. So to go over some key findings before we get into the rest of the experiment, the two parameters that we were looking for that will be explained in more detail shortly were n and mu. So the n value was found to be negative 2.8501, and the value of mu was found to be 2.854. Some relevant background we'll need to know before we get into the lab starts with the Biot-Savart law, which relates the magnetic field at a point for a tiny current element where the charge of that element is described by Q, and taking the cross product of the position and velocity vectors can yield the magnetic field. Additionally, the magnetic field of a dipole will be important, where you can think about a dipole as a closed circulation of an electric current system, where that value of mu is the one we will be showing how to find throughout the lab. And then lastly, the distance-dependent formula will be important. And as you can see on the right-hand side of the bottom, it can be linearized, which will be important in determining the relationship there. The two assumptions made during this lab were firstly that the bar magnet acts as a dipole, and second, that magnetic field falls off as the distance increases, as shown by that distance dependence equation. So now we'll go through the methodology. For the experimental procedure, you'll first want to make sure to orient the phone's magnetometer perpendicular to Earth's magnetic field, which was done using an app, and then determining the location of the phone's magnetometer chip, and then lastly to measure the distance between the magnetometer and the bar magnet for both on-axis and off-axis orientations. So a depiction of that process can be shown on the right-hand side, where the system is the bar magnet and the surroundings are everything else. Since I was using my phone to do the experiment, I couldn't take a picture of the actual setup. So now going into the results and discussion, and then further discussing the computational model. Here are the results for the on-axis measurements, where the distance and the magnetic field were measured for different distances, and then that yielded the graph and resulting linear fit equation shown on the right, where through using that distance dependence equation talked about previously, the value of n can be found. This is the results for the off-axis data, where similarly distance and magnetic field were measured after moving the phone up perpendicular away from the bar magnet, as depicted in the top right image. Then using the linear fit equation from the data calculated during this lab, the value of n is the slope of that line, and then the y-intercept represents the log of the k constant. So then on the right-hand side, isolating k by gives us a value of 5.71 e to the negative 7, which can then be put into the magnitude of magnetic field, and by rearranging that with algebra, we get that mu equals 2.855. So then using that value of mu that was found from the physical experiment, a VPython model was created, where first the magnetic field had to be created by a function, and then both on-axis and off-axis arrows were created for the fields. And then lastly, this plotted the various arrows together, which resulted in this, where the magnetic field was similar to that observed in the lab. So there were a couple of potential sources of error, one being that the other magnetic objects nearby could have affected the accuracy of the measurements, and then also there was probably some error in the precision of finding the exact magnetometer location. So to summarize the key findings again, the value of n was found to be negative 2.85, and then the value of mu found to be 2.855. So then out of all the observations that were listed here, only the first and fourth ones were observed in this lab, which was in line with the distance dependence relationship that we knew to be true. So then what if the experiment had been set up such that there was some intermediate angle, this would have caused less accurate results, as Earth's field would have interfered with the bar's magnetic field. And then if there were two magnets connected end to end, I would expect that the magnetic field would double, but since they're lined up end to end, the direction would remain the same as it did for this experiment. Thank you.